Myself Nilesh Kumar, Assistant Professor of Government Engineering College, Rampur. I am presenting you the lecture on semiconductors. And of this video session you will learn following things: the semiconductors, intrinsic and extrinsic. Intrinsic semiconductors, bonds in semiconductors. The atoms of every element are held together by the bonding action of valence electrons. This bonding is due to the fact that it is the tendency of each atom to complete its last orbit by acquiring 8 electrons in it. However, in most of the substances, the last orbit is incomplete, that is, the last orbit does not have 8 electrons. This makes the atom active to enter into bargain with the atoms acquire 8 electrons in the last orbit. To do so, the atom may lose, gain or share valence electrons with the other atoms. In semiconductors, bonds are formed by sharing of valence electrons. Such bonds are called covalent bonds. In the formation of covalent bond, each atom contribute equal number of valence electrons, and the contributed electrons are shared by the atoms engaged in the formation of bond. For example, the germanium atom has 4 valence electrons. It is the tendency of each germanium atom to have 8 electrons in the last orbit. To do so, each germanium atom positions itself between 4 other germanium atoms as shown in the diagram. Each neighboring atom shares 1 valence electron with the central atom. In this business of sharing completes its last orbit by having 8 electrons revolving round the nucleus. In the way, the central atom set up covalent bond. Extrinsic semiconductors. In intrinsic or pure semiconductors, the carrier concentration of both electrons and holes at normal temperatures are very low. Hence, to get appreciable current density through the semiconductor, a large electric field should be applied. This problem can overcome by adding suitable impurities into the intrinsic semiconductors. The extrinsic semiconductors are those in which impurities of large quantities are present. In general, the impurities can be either third group elements or fifth group elements. Based on the impurities present in the extrinsic semiconductors, they are classified into 2 categories. 1. N-type semiconductors and 2. P-type semiconductors. N-type semiconductors. In order for silicon crystal to conduct electricity, we need to introduce an impurity atom such as arsenic, antimony or phosphorus into the crystalline structure. These atoms have 5 outer electrons in their outermost covalent bond to share with other atoms and are commonly called pentavalent impurities. This allows 4 of the 5 electrons to bond with its neighboring silicon atoms, leaving 1 free electron to move about when electrical voltage is applied. As each impurity atom donates 1 electron, pentavalent atoms are generally known as donors. Antimony Sb is frequently used as pentavalent additive as it has 51 electrons arranged in 5 shells around the nucleus. The resulting semiconductor material has an excess of current-carrying electrons, each with a negative charge, and is therefore referred to as N-type material with the electrons called majority carriers and the resultant holes minority carriers. P-type semiconductors. In contrast of N-type of semiconductor, if we introduce a trivalent impurity into the crystal structure, such as aluminium, boron, or indium, only 3 valence electrons are available in the outermost covalent bond, meaning that the 4th bond cannot be formed. Therefore a complete connection is not possible, giving the semiconductor material an abundance of positively charged carriers known as holes in the structure of the crystal. As there is a hole, an adjoining free electron is attached to it and will try move into the hole to fill it. However, the electron filling the hole leaves another hole behind, and is forth giving the appearance that the holes are moving as a positive charge through the crystal structure. Conventional current flow. As each impurity atom generates a hole, trivalent impurities are generally known as acceptors, as they are continually accepting extra electrons. Boron B is frequently used as trivalent additive as it has only 5 electrons arranged into shells around the nucleus. Addition of boron causes conduction, which consists of many of positive charge carriers, results in a p-type material, and the positive holes are called majority carriers while free electrons are called minority carriers. Thank you.